I'm not happy with a 4-component model, if I want 2, I cannot look at these ones. I have to estimate a 2-component model. Everything changes. So Parafac is much more complicated than, for example, PCA. When I do PCA, I generally don't care about the number of components. I just take 10 components and I look at the first ones. And that's fine. In Parafac, you cannot do that. In Parafac, you have to use the right number of components. If you want to have this chemical interpretation, you have to find the right number. And if you don't, it's not going to make sense. If you don't, what you find is not going to be chemically meaningful. And that makes Parafac much more complicated than PCA. That's the price we pay for being able to find pure spectra. So we kind of have to live with that. It would be nice if it wasn't like that, but we have to accept that. And that means that in Parafac it's much, much more important to determine the number of components than, for example, in PCA. We have to spend much more attention to that. So we need to talk a little bit about that. But first, I would like to show you, actually I want to show you a little illustration, just an alternative illustration of the Parafac model of these data. Let me just see if I can find that. Here we are. And don't worry about what's going on. I'm going to make a beautiful picture that doesn't actually look so beautiful at first, but let me explain it. So what I'm just plotting a Parafac model of this data set, but in a slightly complicated way. This is sample 1, 2, 3, 4, 5. So these are my 5 different fluorescence samples. Now remember, I was using 3 Parafac components. This is component 1. So in component 1, let me just get this. So in component 1, I'm finding a pure emission and a pure excitation spectrum. And that's going to be the same for all samples. This is actually the tyrosine sample, I believe, tyrosine analyte. So it has the same spectrum in all the samples. The only thing that differs is that I'm finding a score vector. I'm finding a score for each sample. This one had a high score. If you remember, we looked at the score. This one had a 0 score. So I'm taking the same landscape, multiplying by 0, and here also 0, and here some other values. So all of these have exactly the same shape, but are scaled differently. That's just the Beer's law. This is my Parafac component 2, and it's the same thing. It's a different excitation and emission spectrum, but it's the same for all of them. The only thing that differs is that they have different concentrations, different score values, and likewise here. If I take all these 3 and subtract them from my measurements, then I have my residuals. So the residuals are simply these ones subtracted from the measurements. And that goes for all the other ones as well. So I think this is kind of a nice visualization of what the Parafac model is. Now you can see that I have something strange going on in the data here. Well, that's actually the Rayleigh scattering. And we'll talk more about that later on. But it's nice to have an understanding of what the Parafac model is doing. For example, if you're working with fluorescence, in terms of the fluorescence. It's a very chemical model, in fact. Okay, let me get back here. So I can do all these plots here as well if I wanted to, plot the scores and the loadings and residuals, but it's just easier to do it here in MATLAB for me. Okay. Oh, sorry. It's complicated. unfortunately, we have to talk a little bit about the algorithm. How do we find the scores and loadings? In PCA, we never worry about that. Because in PCA, when you push the button and ask for PCA, you get PCA. In Parafac, when you push the button and ask for Parafac, sometimes you get it. Other times, the algorithm will decide, I'm going to give you something else. And this is really annoying, and that's another complicated aspect of the Parafac model. And that means we have to understand a little bit about the algorithm if you really want to work with Parafac. And that's annoying, but that's how it is. It's also the reason why mathematicians, they really don't like Parafac. They think it's kind of scary. They really prefer the other PCA, which is the Tucker model. We haven't talked about that, but they like that much more. And the chemometricians hate that because they think it's complicated. So, anyway, Parafac is nice and it's very chemical, but its algorithm is far from perfect, so we need much better ways to estimate the Parafac model. So I'll explain how the algorithm works. You don't have to sort of get the details, but you should sort of get the concept. And I'll start by showing you how we can find scores and loadings if we're doing something like PCA, if we want to find a bilinear model. So like this, let me write it in matrices as well. So what I have is that I have my data X, and now I want to find A and B. Well, my handwriting is not good. Okay, so how can we do that? That's a complicated non-linear problem because it's a product. But I can separate it into two simple problems. Because if I know what A is, or just plug in some random numbers and say, this is my guess. So now I have guessed what A is. It's wrong, but I guessed something. Then finding B is actually a least squares regression problem, just like linear regression. And it's solved like this. And this is simple. So I turned the complicated problem into a linear problem in B, and I can solve that very easily. So now I have a guess on what B is, and now I can get a better guess on what A is, because now I can plug in B and estimate A by least squares. And now I have a better guess on A, so I can go back and improve B. So I do A, B, A, B, A, B, until nothing is happening. That's called alternating least squares. And that's actually what we use for Parafac, but in a slightly more complicated way. It's also not a very good algorithm. If you talk to people in the optimization literature, it's what they call the naive approach, and that's not a compliment. That means it's the most stupid kind of optimization you can do. But it's very difficult to come up with anything better for Parafac in general. So in Parafac, we don't have A and B, we have A, B, and C. But we do exactly the same. We just have 3 lines here. So A, B, C, A, B, C, A, B, C, A, B, C. And I'll show you the algorithm, but it doesn't look nearly as nice. Again, because of the problem that matrices don't work for three-way arrays. So if I'm forced to writing the Parafac algorithm with matrices, it looks like this. It makes no sense. But what it does is that it's updating A and B and C in a very strange way. But anyway, what it shows you is that you can actually implement Parafac like this in MATLAB. If you're good at MATLAB, you can write these 5 lines and then you have a Parafac algorithm. So that's nice. This is actually C, but we have to represent C as a 1 row at a time. So this is 1 row of C, and you go through all the different rows. Never mind that. The main point here is to see that's 5 lines, not to see how it actually works, because that's complicated. But that's the notation. The principle is simple. I'm solving a least squares problem for A, B, and C. It's multiple linear regression as we've been doing in high school. It's the same thing. And the advantage of this, well, there are many advantages of this. It's very simple, even though it looks complicated, but it is simple. It extends very easily to n-way. So that means I can do 5-way analysis, etc. Parafac, in the toolbox doesn't care about whether it's two-way or three-way or nine-way. We can do it easily. Actually, we can also easily handle missing data and do more advanced stuff like adding constraints. If we want to force the model to make things look non-negative, or we want to force the model that there's only one peak, that it's unimodal, or we want to have sparsity is very popular these days, if we want to impose sparsity. All of this is easily done because it's simple linear regression. So you just take the results from linear regression and you apply them inside the algorithm. Now I would like to exemplify the missing data, how nice we can handle missing data. Let's see. And let's close this one. I really made the font too big here. Okay, I have to do some nerdy stuff now. So, what I want to show you is that Parafac does not care whether we have missing data or not. So I'm going to take in my three-way array, I'm going to take different elements here and set them to missing and show you what will happen. So let me see, we can do I will count the number of elements and then I will take the first 1,000 in randomly selected. Let's say like this. Now I do a random selection. Of the first 1,000 elements, and I set those to missing, and let's see if I actually did what I think I did. Missing is called not a number. Let's see. I did not. Stop. Getting closer. Alternating, exactly. Now you see, now there's holes in my data. So 1,000 holes out of 60,000 elements. But with Parafac, what we can do is that we can actually just, and this is really beautiful actually, we can put in some numbers and then estimate the model and put in better numbers and continue doing that. And let me show you what that will look like. So if I do Parafac on this data set, actually let me just do it here. It's gonna say that there are 1.6% missing data. Well, that's fine. In this window here, I can check the loadings. They look exactly the same. Okay, so let me do more. Let me do 16%. That's a lot more. Now you see, now it's beginning to look a little bit scary. So let me try and fit a Parafac model to that. You see, it looks exactly the same. There's no difference, even though we now have 16% missing data. Okay, so let's go a little bit crazy. Let's do half the elements. Now it's worse. Let's see what will happen. Again. Parafac really doesn't care about this. Whoops. It really gives me the same solution. Okay, let's do one last one. Let's do 54,000. That's gotta be a lot. there's hardly any data left. The majority of elements are not measured, are simply missing. And let's see if it works. So now I have 90% missing data. And it still makes no difference. Well, it's getting a little bit noisy now, you can see, compared to before, but it's really impressive how well I can actually model the data here. And that's really the beauty of Parafac. It's because of the structure. It's because I'm estimating these loadings in 3 different directions. It gives an enormous robustness compared to when you unfold your data. And in this case, it's not really it sounds impressive that we're missing 90%, but the real deal here is what information is present, not how much we remove. And even when we only have 10% left, we still have enough information to estimate these things reliably. But the Parafac model is way more robust than a PCA model, for example. So we can do another thing just for fun. We can try and add noise instead of removing elements. So let me do, let's see, let's say, that's how the data looks normally, right? Now let me add noise to the data. The resonance data is kind of nice. So let me add, it's not very noisy, but let me add some random noise. And never mind all the things I'm doing here in MATLAB. It's just, I speak MATLAB very well, so it's easier for me to do things here. Let's say 100. Okay, that's a noisy version of the data. You can hardly see the peaks anymore. Let me try and build a Parafac model on that. See here, I get the same thing. It doesn't look nearly as noisy as the real data because I'm averaging over many components on many directions, so I get a huge noise reduction. We can even try and add more noise, I don't know. This is twice as much noise. Wow. Don't know if that works. We'll see. It still works. That's fine. Okay. So you see, I can add huge amounts of noise, and the parameters that I estimate are much more accurate than the real data. Now remember that the Parafac model, let's do this. This is the Parafac model plus the noise. I can actually model, I can write the model of the data, I can multiply these things. Like this. And that is really my model of the data. So I have a landscape that I measured, and then I have the model of that landscape and the residuals. So for every sample, I have a model of my landscape. If you look here, this is my model of sample 1. This is the actual measurement. This is the data that I used to find the model, and this is the model. You see, the model is way better than the raw data because it removes a lot of the noise and puts it into the residual. Okay, I think we need a little break, maybe, and then we'll continue. How long is an official Okinawa break? 10, okay, take 10 minutes.
I think you have a forward version.
I do, so how long time do I have?
Have you been talking about the raw material?
No.
Tomorrow. No, you have to work today more.
Yeah, but we do a break now.
But more afterwards.
I know. Yeah, I have to talk until 12, right?
Tomorrow. Tomorrow.
Oh.
The afternoon you have to work.
I'm completely lost. Let's take a break and then I have no idea.